Uh, so we have exam 1 coming up early next week. So our next class, in fact, Monday, March 1st is going to be your exam 1. We are not going to have any new lecture on exam days, both for exam 1, 2, and of course the final. I have created a new section on Piazza that has documents regarding the logistics for the exam. I've also uploaded a back exam from last spring. And the content that is going to be appearing on exam 1 is lectures 1 through 9. So the lecture content for today is going to be part of the exam, but only to a limited extent. It'll mostly focus on MIPS coding, MIPS ISA, the initial few concepts, CPI, processor performance, and so on. What are we doing today? Well, we are going to be talking about processor data path, which essentially means what are the various components that are going to be involved in order for the instruction, any instruction, to start and finish. Of course, we are going to be needing an ALU to perform the operation itself, to execute the instruction itself. We are also going to need to increment program counter by 4 every time we move down one instruction. We are going to need to incorporate for load word and store word instructions that are with respect to the memory. So all those components that we are going to have to manage in our data path in order for instructions to get completed, that's what we are going to be focusing on. If there is an instruction, for example, add, what all does it take in terms of hardware for it to get completed? So a few steps for designing a data path. Well, the first thing that we are going to have to refer to is the instruction set architecture itself, meaning what are the instructions, what are the formats, R type, I type, J type, are we limiting it to a smaller set of instructions or not? So all of those things we are going to need to explicitly think about, right? Put one real register for each register in the ISA. So suppose you have 32 registers in your ISA, then you're going to need 32 real registers in your register file, which will eventually be in a hardware form. And we are going to also probably need a few more for internal use. And then we'll put interconnections so that we can have register to register transfer. We're going to need to select data path components. What are a few? Multiplexers, ALU, buses. All of those fall under the category of data path components. We are going to next assemble the data path in order to meet the requirements of instructions getting executed. So, the 5 steps in the life cycle of an instruction that we've been talking about, starting from fetching the instruction to incrementing the program counter, all of those 5 steps, we are going to need to see what components we are going to need. And the general design principles that we are going to have to be aware of are a couple of them. Make the common case fast. So when you're putting things into hardware form, you're going to keenly observe what are the common instructions, and you're going to wire those up or connect those things, assemble the data path in order to make those common cases as fast as possible. The next one is we are going to stick with a simple and regular instruction set, which essentially leads to a faster data path. So just for the sake of discussion, we will consider a simplified MIPS instruction set architecture. In other words, let us try to limit the instructions that we will worry about to a few, right? Maybe 8 of them, and then see what goes on into the assembly of the data path so that we can build on that understanding. So we are going to consider our MIPS processor in a simplified form. Let us suppose we only have these instructions. The first 2 over here are memory reference instructions, because only those instructions we would need to bring data from memory to the register file in the case of load word, and store a word from the register file back to the memory. So those are called the memory reference instructions. So only those two we will consider for this particular discussion. Arithmetic logical instructions, well, we can have add, subtract, or, and set on less than. We have actually seen, the types, which categories they fall in, R versus I versus J. We have looked at the reference sheet. We know that it is there, and if you want to know more about these instructions, we can always refer back to that to get the very down to each and every bit location details for these instructions. Then in terms of control flow, we will have branch when equal. We will also include J later on, the jump instruction. So let us actually just do one step. How many instructions are we talking about? We have 1, 2, 3, 4, 5, 6, 7, 8. Right. So far we have 8. We are going to include J later. So right now in the simplified set, I'm looking at 8 instructions. So how many bits am I going to need to identify between these 8 instructions? 3, right? So in this simplified MIPS ISA, I essentially need only 3 bits to identify one instruction from the other. So keep that in mind, because you are going to see this number appear for the ALU opcode option that we will have. All right. So basic steps for each instruction. Well, what are they? Well, we know that the life cycle has 5 instructions, but if we simplify it down even further, it essentially starts with fetching the next instruction, which is going to be at a particular address location, right, in the memory. We're going to get that to our program counter, because program counter will be the register that should contain the instruction that I'm working on, that I want to work on next, right? So I'm going to fetch that instruction from an address location to the program counter. So that's step 1. Next, if I need to fetch some operands, I may need to read some registers. I'm going to use, maybe most likely, an ALU to execute the instruction. And the last step, which is called the housekeeping step, is to update the program counter. Essentially means add program counter PC equals PC plus 4, and that's it. Now you're pointing to the next word, which is essentially where the next instruction is going to be. Right? So that's it. And then you cycle around, right? You go back. The life cycle gets complete. Now it's an infinite loop, and you go back to fetching the next instruction, unless our instruction is kind of a jump instruction or branch on equal instruction. That's when your program counter doesn't go step by step. It can jump around. Now let's spend a couple of minutes kind of reviewing the MIPS ISA. This all things on this slide should be essentially review. So we'll go through it pretty quickly. All instructions are 32 bits long. We have talked about instructions being word aligned, right? You've heard me say that many times. Instructions or programs are word aligned. We cannot start an instruction midway through a 32-bit sequence, midway through a word. We have to have it start and finish along the word edges. There are 3 types of instructions: R type, I type, and J type. R for register type, I for immediate type, and J for jump type. We have looked at each of their formats earlier. We are not going to worry about the J type today, so we can just focus on R and I type instructions and their corresponding assembly of the data path components. Each of these fields has a specific meaning as far as the data path is concerned. OP stands for the operation, right? That's how we identified the types, distinguished the types using the OP field, which is 6 bits long. The next one was these 3 registers, right? RS and RT being the source registers, and then RD being the destination register. So those are your 3 registers, 2 of them being source registers, and 1 of them is the destination register. Now, depending on if you are working through an R type instruction or an I type instruction, we may have RD field, or we may not have the RD field. Then the last two fields over here, there's a shift amount. So if you are doing a shift left or shift logical left, then you have a shift amount. So you could specify how much you want to shift in that field. And then we also have the function field, which is to cover the variations within an operation. So for example, if you have add, then you can use the function code to distinguish between add and add unsigned. So they both have the same OP field, opcode field, but they have a different function field. Now, as far as I-type instructions are concerned, we still have OP field, we still have RS and RT playing our two source registers, and then we have a immediate offset, which was used for providing the immediate constant directly into the instruction itself, or maybe a offset address, 16-bit offset that could be added to a base register which contains the base address. So all of that goes part of the I instruction, right? And then for the last one is target address, which is essentially for the jump instruction. If you wanted to jump around in your memory to start execution of an instruction at a different place, then you can use that jump instruction. We'll be focusing on R and I today. Now let's talk about the register transfer language description of basic instruction. So how does data move from one register to the other in order for these instructions to be executed, right? So if you think about the first step in almost all the instructions, for all the instructions, it is the instruction fetch. I need to get the instruction into my program counter. So what is that RTL notation for that step? I'm going to take a look at the memory. The address in the memory is going to be referenced with respect to the contents of the program counter. And then I'm going to move that, indicated by the arrow here, to the instruction register, right? IR. That's your instruction. That's fetching of the instruction. Now, in terms of execution, how does it look like? And these are the kind of details that you will see in your the MIPS green card reference sheet as well, right? So for example, if you look at add instruction, if I zoom in, there are two things involved. One is to add the contents of the two source registers and put the result into the destination register. All of these things are happening in the register file itself. And then of course, after you're done with that add instruction, in order to do the housekeeping, you would also need to add 4 to the program counter. So, but if you just look at this, right, let's try to understand what are we going to need to do this add and what are we going to need to do to this add. What hardware components are we going to need to do those things? I hope you guys say ALU for this, right? ALU, yeah. But in order to do the +4, I can have an adder that has 4 as one of the inputs, right? It's hardwired to 4. So I can just take current PC and use an adder to just add 4 to it. I would not need to use the same ALU, right? Because if I started to use the ALU for even this adder process, then first thing, I will have issues with pipelining. I will not be able to do pipelining. That's something that we are going to learn later on. The idea is I will not be able to run multiple instructions in parallel. I will not be able to do that. So, I almost have to choose a different adder that is adding a constant 4 for that, but I'm going to need an ALU definitely for that. Similarly, over here, I need a subtractor. I need that same adder. For the immediate OR operation, why do you do PC +1 when you do PC +4? No, you do PC +4. PC +1 is sort of, a conceptual thing. It's incrementing PC by 1. What that really boils down to for the MIPS architecture is incrementing PC by 4, because you're not looking at the next byte, you're looking at the next word, which is 4 bytes. Right. So it's with respect to the MIPS architecture. But no matter if you do, in both those cases, PC plus 1 or PC plus 4, you are essentially talking about the same thing, pointing to the next instruction. So PC plus 1 is not realistic. Yeah, it may be realistic for a certain memory architecture, but for MIPS, where we are considering things to be 32 bits long, instructions to be 32 bits long, we would need PC plus 4. So it's more about the ISA and not about the whether you need to add 1 or 4. It's directly related to the ISA. For the MIPS one, word aligned 32-bit instructions, so I need to add 4. Okay. Remember, you see, PC is an address, right? So in order to point to the next address, I would need to add 4. I kind of have, isn't PC? No. So program counter is an address, right? Whatever address you have for a location, say over here, so if this is X and there is 1 here, 1 byte here, 1 byte here, another byte here, those are 4 bytes. If I come down to the next one, it would be X plus 4. Right? And that's what I would update the program counter with. But if I multiply the whole thing by 4, then it's like 4PC equals 4PC plus 4, isn't it? Right. All right. So let's see, where are we? All right. So in terms of OR immediate, and we are going to need some other things. So for example, if you're doing this logical OR operation, we are going to be ORing whatever you have in this source register RS with a 16-bit 0 extended immediate. Let's talk about what that 0 extension means. As far as the load and the store word are concerned, and in fact even the branch when equal, you do a sign extension. So there are two terms here being mentioned. One is sign extended and the other is 0 extended. What is the difference between the two? And why are you using 0 extended for OR, and then why are you using sign extension for things like load, store, and branch when equal, right? So let's talk about that. But first, we will do a discussion on what is 0 extension and what is sign extension. So 0 extension. Let's see, there's a question in the chat box. When we are writing MIPS pseudocode on the test, should we use PC plus 1, PC plus 4, PC plus 4? MIPS, you always say PC plus 4. It's directly related to the ISA that we are considering. PC plus 1 is sort of a generalized idea, right, to increment program counter. I hope that answers that question. 0 extension and sign extension. Let's talk about that. So suppose we have, say, 4 bits, right? So suppose we have B0 and B1 and B2 and B3. I'm just assuming that it is a 4-bit number, which is also there for this guy as well. And I want to extend it, 0 extension, to 8 bits, right? So 4 bits, I want to extend it to 8 bits. So the question is, how do I do that with respect to 0 extension, and how do I do that with respect to the sign extension? Right? Each of these are bits. So we just write that. Bi belongs to 0, 1, where I equals 0, 1, 2, and 3 in this case, right? So 4 bits, each of these are like 0 or 1, right? So if I wanted to extend that, let's talk about the first case now. If I wanted to extend that for 8 bits, what should I do with 0 extension? The name gives it away. Add zeros to the left. How many? Just add 4 zeros to the left. 4, right? 4. So if I add 4 zeros to the left, I would have 0 extended the number to 8 bits, right? And why is it that I'm doing it for OR? Why does it work with OR? Because if you have any 8-bit sequence here with which you're ORing this guy with this guy, you have to 0 extend it. If you had ones over here, you would get ones at the output, right? You don't want this to matter, which is why for OR immediate you do a 0 extension and not a sign extension, because the sign could have been a 1 too. Let's talk about sign. What should I do here in blue? For AND, would it be once? For AND, if you want to do, yes, it would be once. For AND immediate. Let's see, add 4 of whatever B3 is to the left. Yes, you got it. So I would do B3, 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 and B3, right? And over here, if this was a positive number, then it continues to be a positive number. And if this was a negative number, it continues to be a negative number. And we have seen that using 2's complement form, when you do that sign extension, we actually talked about it in terms of how you prevent overflow from happening if you do that. But that's what it's sign extension, right? And in the context of load, store, branch when equal, you're doing sign extension as opposed to 0 extension. Why? Well, I hope you guys agree that when you are loading an address or storing an address or storing a word or branching, that particular offset data may not be unsigned. Yes, data is signed, right? That data is signed. So you may want that offset which gets added on to an address to be positive or negative, right? So if it is positive, then you are referring to the target address is greater, right? So if you are let's see, if B3 equals 0, what does that imply? That implies that as far as load and store instructions are concerned, target address is greater than base address, right? Base address is essentially the address in one of the registers, and then you add the offset to it. And if the offset is positive, then the target address is going to be greater. And in the other case, if B3 is 1, that implies that it is a negative offset. Your target address is going to be less than base address. You guys see that? So it's relative to the address mentioned in the register, one of the register. So you may want to do that target address smaller than that or bigger than that, which is why you can use that as a signed number, and you do a sign extension for that. You don't do a 0 extension for that. Questions about this concept of the difference between 0 extension and sign extension, and why what happens to the target address in relationships to the load, store, and branch when equal instructions? And you kind of, you can validate all these statements by when you look at this, right? Like, so you see, if you look at the load instruction, what do you have? You have whatever you RS, that was the base address. You added the base address to this offset address, could have been positive, could have been negative. When you added them together, you got the target address in memory. That's what you moved into the RT register. That's what you do for load word. And for store word, things are opposite. You still have the base address in RS. You still have a signed 16-bit offset provided here. You add them, and whatever you have in the register RT, you store it at that particular target address location, right? So let me just talk about these two here. This one and this one, those are essentially contain target base address, right? And then you add the signed constant to it. And then, of course, after you get done with the instruction, you also do the PC equals PC plus 4. As far as the branch when equal instruction is concerned, oh, by the way, what do you need to do this? Zero extension. I need something that can do a zero extension in terms of hardware. I need some hardware to do the sign extension. Let's see. I need something that I should be able to read from and write to memory, right? So over here for load, I'm reading from memory. For store, I'm writing to memory. So when I put memory as part of this data path or in along with this data path, then for load and store word, I also need controls for my memory, right? Whether I'm reading or writing to execute these load and store word instructions. So ALU needed, add 4 needed, zero extender needed, sign extender needed, and memory references, memory read and write controls are needed so far. Let's see. For branch when equal, what do you have? You have first a condition. You are going to compare the contents between RS and RT. And if they are equal, then you do PC plus 4 plus a sign extended value. But the problem is PC plus 4, that was coming out of this address. We need some sort of a multiplexer to either do PC plus 4 or do PC plus 4 plus the sign extended value. So a multiplexer also comes into the picture now, because you're choosing one when they're equal and you're choosing the other when they're not equal to update the program counter. Else, if they're not equal, then program counter just goes to the next instruction, which is PC plus 4. Right. So now we have put in mux as well. Now let me talk about this condition here. How are you going to do this comparison in terms of hardware? How can you execute this condition? RS equal to RT. What component are you going to need? Be as specific as you can be. Logical comparator does it for you? Yes, absolutely. But can I use something else to do it? Because comparator is sort of a little bit more complicated. Can I do it in a very simple manner? Maybe something arithmetic? Exclusive OR also, right? So exclusive OR, exclusive NOR, these are all kind of pointing towards a comparator, right? These are all pointing towards simplified version of a comparator, but it is a comparator. But kind of zoom out and think about this. You are just trying to compare the contents of RS and RT, right? Can I do this? Can I do just a subtraction? I will just do a subtraction between the contents of RS and RT, and if it is equal to 0, if the result of that subtraction operation, which I can perform using ALU very quickly, if that result is a 0, then I know it is equal, right? If it is not equal to 0, then I know it is not equal. You guys see that? So this one doesn't need the comparator, doesn't need the exclusive OR, nor a lot of hardware. It just needs a subtraction operation to happen, which is pretty straightforward, and there is already like hardware for it, right? Like we already have the ALU that can ALU faster than even an exclusive OR. So ALU in general has to have all these components, right? So ALU has to have all the hardware that supports arithmetic as well as logical operations. But if you want to do like a 4-bit exclusive OR versus 4-bit subtraction, then you just need a subtractor for that, right? Like the ALU, the first few operations, one of the basic ones is subtraction, right? So in terms of you know, implementing it, it becomes very streamlined. All right, let's move on. So that's one idea, right? The way I can check for this is by using the ALU and monitoring the zero result, ALU result being 0 or not. Okay, so for that I also need the ALU. So I hope that discussion was good. Now at least we know what are the different components you would expect to see in this data path, right? ALU, add by 4, 0 extender, sign extender, again ALU here. Also an important thing to note here, when you are branching, the offset is in words. When you're branching, offset is in words. Offset is in words. However, when you are loading or storing, the offset is in bytes, which is why I don't need to multiply it by 4. But when you're looking at the branch when equal, you would of course branch to something that is word aligned because it's an instruction. That is the reason we would provide the offset in words. How does it know when to branch? That is when to, yeah, if the things are equal, that's when it will know to branch. So when you come up with this instruction, right, branch when equal, if that is the instruction that the processor is working on, it will check the contents of these two registers, and if they are equal, then it will branch to, so program counter will not just go to the next instruction, it will actually go to PC plus 4 plus this sign extended 16-bit immediate that is multiplied by 4. I think that's you. Where, right? Right. So where I need to provide an offset in words, right? So suppose I provide an offset of 2 in words, right? I would take that 2 multiplied by 4. I got 8 bytes, right? 8 bytes, I would add that to PC plus 4. What does that mean? PC plus 4 plus 4 plus 4. So instead of looking at the next instruction, I'm looking at 2 instructions down the line. See that? Or I could have minus 2 for the offset, negative 2. Even then, I am providing that in terms of words. So I multiply by 4, I get negative 8 bytes. So I would go PC plus 4 minus 8. Then I'm looking before the branch instruction. Does that answer your question, Rojan? So when we are talking about the branch when equal instruction, we looked at that example. Where does the 2 go in this line? Right here. Immediate. Yes. So this immediate 16-bit immediate field is what you will provide over here, right? So you will say in words, right? 2, 1, 2, 3, 4, whatever you want to say, but it will be in words. So you will take that, multiply by 4 to get the value in bytes, then you will do a sign extension, then you will add to PC. Okay, let's move on here. We talked about sign extension. Let's talk about the instruction fetch unit. Pretty simple. I just need to get the next instruction. So what do I need for that? I need an address, right? Where is the address? I need it. I need the address is in the program counter. So fetch the instruction from a memory location. The address is provided by the program counter. Update the program counter. You can do that in two cases, right? If you are doing things sequentially, then program counter gets added by 4 or gets updated by current value plus 4. That's sequential, one instruction after the other. Or in the case of branch and jump, your program counter gets updated with something else. Just as we saw, it was PC plus 4 plus some sign extended 16-bit address, right? So those are only the two options that we have. Either you do PC plus 4 or you do PC plus 4 plus something else, and that's what you would update with PC, right? That's your instruction fetch. So what does that mean? You have your program counter, which is a register, so it's clocked. That program counter is going to provide me an address so that I can refer to the address instruction memory. And when I give it the address using the program counter, out comes the 32-bit instruction, and it's a word because it's 32-bit long. That is the thing that was present at the program counter. So if I look at, just drawing the memory out here on the right, I have, this is my memory, right? And just to keep things distinguishable, I'm going to talk about two different categories of memory. One, instruction memory, the other, data memory, right? So one part is just for the instruction and the other part is where all the data is. All the operands are, where I'm storing all the results and so on. So if this was some instruction memory, then my current program counter is essentially pointing to, let me highlight this. My current program counter is essentially pointing to the address of the instruction, right? So whatever is over here will be coming out, right? So I will give you an address in the program counter, try to access the instruction memory, and when you read that particular address, you will get the 32-bit instruction at that address, right? So that's your PC right there. PC is pointing to the address of the next instruction that you want to execute. Now, you just don't do it once, you have to do this as long as you keep getting instructions. And we said we have two options. One is to do it sequentially, or do it using a branch or jump, which means I need some combinational logic that allows me to compute the next PC contents, next address. Now, this could be, right, there are two options here. One is this could be that, or this could be that. Two options. But no matter what that is, it is going to be a combinational logic. I'm expecting it to have a multiplexer to choose one option versus the other. It is definitely going to have add by 4 somewhere in there, but that's all of that is going to go into the next address logic to update my program counter. You guys see that? So I'm just going to remove the arrow over here because that can be confusing. That is essentially the instruction, right? So even better is going to be to not do shade like this, maybe shade with blue. Questions about this? How does the instruction fetch unit work? And again, I have a clock which is essentially controlling when that program counter can change, right? I'm not going to keep updating the program counter unless I move from one instruction to the other. Because remember, from Coco, a register, a program counter is a register. What does it have? It has a bunch of data flip-flops, D flip-flops. They are all clocked components. They are all edge triggered components. No more questions? All right, so let's move on. What are the combinational components? And we have been kind of, talking about them without looking at them. So let's take a look at them. The first one, of course, is our ALU. And like I said, because we are looking at only 8 instructions, I'm just going to need 3 bits to do the ALU control. Maybe I have 000 for add, and then 001 for subtract, 100 for branch when equal, and so on, right? But I will only need 3 bits to let the ALU know what operation I wanted to perform between A and B. Those are my operands. This is my ALU. The outputs of the ALU, one of them is 0. Where could I use this? I could use that for the BEQ instruction. Remember, you just needed to subtract it and check whether the result is 0 or not. I can use that for that purpose very easily, right? And then the other one is, of course, the result. Suppose you are trying to add or multiply and whatnot. That is going to be your result. So 2 outputs, one of them is 0, that goes along with, the branch when equal. BEQ instruction can leverage that output. And then, of course, we have the result. So that's your ALU. Next, you have an adder. And this is a general adder. This is not just adder by 4, right? This is the adder in which there are 3 inputs, 2 outputs. A, B, these are your 32-bit inputs. The other is a initial carry in. And then you have a 32-bit sum as the output and your final carry out as the output as well. This adder, we may be needing this adder to increment the program counter by 4 or to do some other things. We will use it at different places. You will see that in a few slides. We of course need multiplexers to choose one from the other. For example, I have 32 registers to pick from. Which one should I pick? Well, you tell me using the 5 select lines. I hope you guys agree that I need this select lines to be 5, right? For our case, in the example that I just said, if you wanted this to be like a selection of RS or selection of RT, you have 32 registers to pick from. You are going to need 5 bits to pick out of 32 choices. So your select lines will be 5 for that particular selection. But in some other cases, they may not be 5. They may just be 1 bit. So, which is why we are not writing 5 over here. We are just writing, those are going to be our select lines. So depending on how the MUX is being used, you may have 5, or outside the register file, you may just need 1. But no matter what it is, MUXes will have a bunch of inputs, and if the select line is 0, A will go through. If the select line is 1, B will go through. You've seen this, the idea of a MUX before. But you will need that. Next, you have the shift by N. Why do I need this? Shift by N. Why do I need this 16-bit input and a 32-bit output using a sign extender? Similarly, 16-bit input, 32-bit output using a 0 extender. Why do I need this? Well, we saw that we needed this guy for load, store, PEQ. We needed the sign extender. For or immediate, we needed a 0 extender. If you wanted to, why do we need this shift by N? For example, if you have shift logical left, you can use that shift by N module to get the logical shift by N. Actually, we are not even using this, right? In our case, we are not even doing shift operation in this simplified MIPS. So why do I need shift by N? That's an important question. Anyone? The answer is here. Addresses are in words, yes. So I need to multiply by 4, right? If I want to multiply by 4, how can I do that? By using a shifter. Left shift by 2, exactly, right? So I will need this for the x4, multiply by 4. Let's see. This was used for PC plus 4. This was used generally for selection, so you will see that at many different places. So I hope that with this, once you start seeing the combinational components that we are going to have, you see how they fit into our instructions as well. More data path components, but these are specifically for storage. So the first one we have are the buffers. We are not going to particularly look at buffers in our data path today, but you will see them in the future, especially when we start looking at pipelining. You will have interstage pipeline buffers that become quite critical for pipelining to be carried out. So that's where you will see buffers. But buffers in general are temporary sort of placeholders for information. So what do you have? You have data in 32-bit, you have data out 32-bit, you are using it as a clocked register, and you can write into the buffer or you write disable. So suppose you wanted to write something to this buffer, you would enable this write signal, maybe make it a 1, and then provide the 32-bit input so that you can write to it. And then whenever you want to read from it, you can read from it. But it is a register, so it's edge triggered component. Next, memory. Memory itself, it is clocked because you want to be able to write or read from memory in a clocked sense, in a time synchronized sense. You can't just do that asynchronously. We have a write enable that can be used to write data into the memory. And when it is disabled, maybe if it is 0, when it is disabled, you are maybe reading from memory. You of course need an address when you're talking about memory, because you need to talk about what memory address you are reading from or writing to. So you need an address, definitely. And then if you're writing, then you need to provide the data to be written. And if you're reading, you will have data that is read from the memory. Next, we come to the register file. So what is register file? We have kind of been talking about the register file as 32 registers, right? But there is a lot more to the register file than just 32 registers. Those 32 registers are part of the register file, but alongside it, you also need to talk about register numbers, data to be written to the register, data that could be read from 2 registers. We can only do 2 registers reading at any time. And then if you want to write data into a specific register, perhaps you are executing the add instruction. In the add instruction, you are explicitly providing the destination register. So you would need to write something to the destination register. In that case, you would provide the data to be written to that register over here, and you would enable register write. 5 bits needed to select one out of 32 read registers. This is for there are 2 cases, right? This is read register 1, read register 2. Why do you need 2 of them? Well, you have RS, you have RT, right? 2 of them. And then write register could be your destination register, RD. Depending on which particular type of instruction you are executing, R type versus I type, these might these might be referenced slightly differently. So you would have to look at your MIPS green card to kind of take a look at which 5 correspond to which one. But I've listed them as if this was a R type instruction. Register 1 RS, register 2 RT. Write register is your destination register RD. I need 5 bits to pick from 1 out of 32 for RS, 5 bits to pick 1 out of 32 for RT, 5 bits to pick 1 out of 32 for destination register. And if my register write is inactive, then I'm essentially reading things, right? So when I'm reading things, I have told you which register to read from. So just provide me the data, 32-bit data that is in that register over here, right? So I can also put 32 over here and 32 over there. So that is the number, and those are the contents of that register. That is the number, those are the contents of that register. That is the number, and these are the contents that need to be written provided register write is enabled. Right. Why do you need to read 2 registers? Well, if you want to add, what do? You bring in 2 registers, read the data here, let them go to the ALU, add them, and then put that result back into the register file. So you would need to do 2 registers, reading on 2 registers. All right, let's move on. Questions here? All right, let's move on here. This is sort of the inside of the register file, and this is for the read operation. Remember, we could also do the write. We will take a look at that next. It's slightly different hardware for reading and writing. So for read, there are 32 registers. That's right there. So those are your 32 registers. For MIPS, N is 32. So you have register 0 all the way to register 31. Those have specific numbers. The details of them are listed on the MIPS reference sheet. They are numbered, and you have 5 bits to pick out one of them, right? So all these registers are going to a MUX. What kind of MUX is it? Be as specific as you can be. What type of MUX is this? I am talking about the size of this MUX. 5:1 MUX. Okay, so this is a 5:1 MUX. But how many bit? Five is to 1. 32-bit MUX. Can I say that? Because each of these guys is 32, right? Oh, by the way, this is not 5. This is 32 to 1. The way it is shown, the dot 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 is not captured, but you see there are 1, 2, 3. There are 32 lines here. You're selecting 1 out of 32 using 5 select lines, right? So this is 5. So 32:1, 32-bit MUX, because each line is 32 bits. So when you read it, you also have 32 bits. You guys see that? Each register has 32. Yes. So there are 32 registers, and each register is 32 bits. Yeah, that is a little bit huge. So you have 32:1. The same thing applies for this guy, right? So even this MUX is, 32:1. You also need 5 bits over here. and then these are 32. That's for the second one. So the same 32-bit registers are an input to the second mux here, and depending on the control provided by the read register 2, you pick one out of the 32 registers. It's a big boy mux. Okay. You guys see that? So when you're trying to read, you have all the 32 registers and you have two multiplexers. Each of them is a 32:1 mux in which all the inputs and outputs are 32-bit. So for example, if you said number 1 here, right, this guy would go here. And if you said number 2 over here, then this guy, the next one, is going to go here. That's how you read. Okay. So also, because we are reading, we can read multiple registers at the same time, and that's what would happen. So you're doing things in parallel. 2 registers at a time, at any time. Next. How about write? Things are going to be slightly different. Over here, we are not going to have a mux. We are in fact going to have a decoder as well as bunch of AND gates. We still have the 32 registers to write to. Now let's talk about the write control and the data to be written. The data that you want to write is provided over here. Register data. That's the one that you want to write to the register. So you have, that is going to be 32-bit, right? This is 32-bit. But it can go here to this guy, to this guy, to this. The data can go into any one of the 32 registers. The wiring provides us with that option. However, you have a register number that is going to activate one and inactivate all the others, right? So that's your decoder, right? Has one active output at any given time. That's your decoder. And it'll take the responsibility of having only one output active at any given time. We have learned that. So you have a n:1 decoder over here. The outputs are 0, 1, all the way down to n-1. When you provide a particular number, say 17 or 5 or 29, whatever register you want to write into, you provide that number over here. It is going to make one of these guys active. The remaining are going to be inactive, which essentially, will have one of these active, right? Only one of these AND gates will give you a non-zero output, which essentially is connected to the clock input of the registers. So only one guy can take things in. Every other things, all the other registers will not be able to clock bits into that particular register. But in order for you to be able to write, of course, you need your write control to be 1, right? So this has to be 1 regardless. So that essentially takes care of the second input for all the 32 AND gates. But what matters here is the number translating into only one output being active. And because only one output is being active, you are essentially going to select only one out of these 32 AND gates to give you an active output. That way, you write only to one of those 32 registers. The data goes to all of them, the 32-bit data. Let's see, can't we replace the AND gates with one AND gate and a demultiplexer? AND gate with a demultiplexer. AND gate with... Right, yeah, you can absolutely do that, yes. There are alternate ways of implementing a decoder. One is to use a decoder, and the other is, yes, it would be definitely more expensive. A lot of discrete gates and a deep multiplexer of the same size, right? Like that size is not going to be trivial. So instead, a decoder is probably going to be a better choice to do this. Also consider that the decoder sort of guarantees you one output being active at any given time, so that you are not accidentally writing to more registers than just one. But if you have more components as opposed to just one decoder, that accident may happen. There are more chances. All right, so when you are writing, you're writing only one register at any given time, and that only happens on the clock edge. Can't we use the write as the enable for the decoder? That way we won't need all the AND gates. If you use write as, let's see. Okay, if you use write, yeah, I suppose you can do that as well. I'm trying to think why it would fail. Uh, yeah, I think you can do that as well. I'm not I'm not sure what that additional AND layer uh, benefits you. Let me think about it. But I think you can do that directly to the clock input. All right, let's move on with data path for R type instructions. For R type instructions, that's your format: opcode, RS, RT, RD, shift amount, and function. Here is our register file that we just talked about. Read register 1, read register 2, write register, write data, read data 1, read data 2. That's the register file diagram with pretty big muxes and decoder. We have already looked at that. Now, at the output, suppose you were doing R type instruction. What does that mean? That means that you are performing arithmetic operations, right? So you would need the ALU. So here is the ALU. You read data 1 from register 1, you read data 2 from register 2, perform the operation, put that result back into the register file, one of those destination registers. So you have 5 bits coming in from here to go to there, 5 bits coming in from there to there, and then 5 bits coming in from RD to go to there. So those 5, 5, 5, 15 bits, 5 of them go here, 5 of them go here, 5 of them go here. So we got the register file into the picture, and we also got the ALU into the picture now. What is a write register? Where is write register? It's not there written over here. It's an additional input. It's not shown here. What is the 0 in the ALU again? So 0 is an additional output of the ALU that lets you find out whether the result of the ALU operation is 0 or not. For example, if you are subtracting equal numbers, then you would get that 0 to become active. Let's see. So what turns it on? All these are powered, right? Are you talking about powering things up? What enables write register? Write register is going to be with respect to when you want to write, right? So for example, it would depend on certain bits from the opcode to indicate whether you want to write or you don't want to write. So for example, if you are loading something, then you are writing to a register file. But if you are storing something, then you are not writing to the register file. I just mean Right. So we are going to take a look at that complete picture here. It may not be connected to a wire directly. It may be coming from a control unit, right? So sort of the mastermind of the data path. Next, data path for load and store. That was for R type. Now we are looking at load and store. So I need to put in a memory block over here right away. Now this picture has the register write that is left as a control that is not connected to anything right now. But we have a few more things that have been added. We now have the 16-bit sign extender module, takes in a 16-bit offset or immediate and sign extends it to a 32-bit value. Why did we need to worry about that? Because we started worrying about load and store instructions. Load and store instructions have a sign extension. Because when you do an ALU operation, for example, you're trying to add this guy, right, the base address will have something in the memory which is 32-bit long, so that goes over here. So it needs to get added with something that is also 32-bit. So you take in the 16, make it into 32, and then you do the addition using the ALU. And then that ALU result becomes an address that you're trying to either read to or write from, depending on whether you're doing a load or a store. If you were writing, then this guy would actually control what you're writing to the memory, and you would also have to enable memory write. If you are reading, then you need to enable memory read, in which case the data that you read from the memory goes back into the register file. That needs to be written to the register file, and you also need to make the register write one. So I've kind of, jumped around, but let me sort of bring things back here. Load and store are I-type instructions. Opcode RSRT and a 16-bit immediate or offset address. No matter if it's an immediate constant or a offset address, it needs to be sign extended to 32 bits because of the load or store. We are going to still use the ALU to perform this particular addition. So our instruction itself is 32 bits, right? These are 32 bits. After the first 6 bits, the rest 5 bits, the next 5 bits are going to go here to identify read register 1. And the contents of that read register 1 will be read over here, will be available over here. RT, that is going to go over here, and depending on whether you are trying to load or store, it goes here as well as over here. Because if you are trying to, for example, here, let me use pink here. If you are doing load, which RT should I highlight? The top one or the bottom one? I'm doing load. If I'm doing load instruction, no, I am executing the load instruction. That's right, bottom one. When I'm executing the load instruction, then I'm bringing things from the memory to the register file, right? I'm loading it into the register file. When I do that, the data moves this way, but I'm doing it on the right data path, which means my RT is going to be the right register, right? So when I'm doing the load, that's where my RT, that's what is referring my RT, right? The RT, these 5 bits are actually picking out which register to write to in the case of load. But in the case of store, what are you trying to do? You're trying to take the data from the register file and put it in the memory, right? You're storing it to memory. So what would happen then? Well, this guy would be RT. This guy would be RT. It would appear over here after you read, and then that gets written to the memory, data memory. You guys see that? So depending on load versus store, this could be RT or this could be RT, right? But then earlier we said for R type instruction, we said RS, RT, RD. Now we are saying RS, RT, RT. Okay, so maybe I can put in a mux over here to select between RT or RD depending on which instruction I am executing. R type, I select RD. I type, or load or store, I select RT. You guys see that? Because RS and RT are sort of consistent between the two types. Only this guy, in this case is RT, in the earlier case it was RD. So I can have a mux before this, and I will add that later on to select one or the other. Now let's talk about what happens when you are storing. Let's do store first, right? So when you do store, things are moving from here to here, right? Okay, so I would need to read. Okay, so when you read, you have one register here, but you actually are more interested in this guy, right? RT, because this is going to be your offset address. You're going to take this offset address. This is your base address. Let me highlight this guy. And in the case of base address, you would take the base address, you would add the offset to it, which was provided in that 16-bit field. How are you adding? You're using the ALU to do that addition, and that computes the target address. Let's talk about target address. This is going to be your target address. And this is sort of the same address as here, right? This plus this. And then that address, along with, what are we trying to do? We are trying to do store first, right? So when you are trying to do store first, which one should I activate? Memory write or memory read? Right. So I would activate memory write. I know the target address. Data goes over there. What data? Whatever data was there in RT. Remember, right? Yes. So that's how the store instruction is going to work out. How about the load instruction? Load instruction, things are going from here to here, right? Add memory to registers. So in that case, well, of course, because we are loading, you're going to need this to be active and this to be inactive. The address is still computed the same way, right? Till the base address, 32-bit offset, add, and then address that you are referring to the memory till the target address. So address works out the same way. No need for write data. It's meaningless right now, right? Even though if it's available, it's meaningless because you're trying to read. And when you read, data comes from here, goes to the write data input of the register file, and if you want to write, you have to make that 1. If you have to activate the register write, in which case you would have completed that load instruction. You have taken the data, read it from the memory, and written it to the register. Which register? RT or RT? Which one? Well, you are doing load, right? So it has to be this guy. So let me sort of highlight this. And for store, it was this guy. All right, questions about this? So I hope you guys see the necessity of all these controls, right? Memory write, used to control whether I'm writing to memory or not. Memory read, used to control whether I'm reading from memory or not. Register write, used to control whether I can write to the register file or not. ALU operation, used to control which operation I want the ALU to execute. And there's a 32-bit instruction which is essentially getting separated into separate fields, 5 bits for RS, 5 bits for RT, 5 bits over there, and the last 16 go there. Memory write and memory read are enabled or disabled by the corresponding machine code to store or load. Memory write enabled or disabled by corresponding machine code to store or load. So a control unit has to send out those memory write and memory read signals depending on the ALU operation code. So there is a ALU control, right? There's a module that would need to look at the ALU control, and depending on whether it's load or store, it would do the memory write versus memory read. So there is still some sort of control unit aspects of this that are missing because, well, we are talking about Datapath. So, you know, the way we are laying out these lectures is first we talk about the Datapath, then we talk about the ALU, then we talk about the control path. So we are going to add more and more to these ideas. Also, I think I didn't mention this. The arrows are bidirectional, right? So in one case you're doing load, in one case you're doing store. So when you're doing store, you're using this guy. When you're using load, memory to register, you're using that. So both are being described over here. And you know, the in my opinion, the really good thing is that both load and store have the same way of computing the target address. Base address plus the offset, and extended offset. Okay, let's move on. The conditional branch. This is going to be quick. This is a branch when equal instruction. It is also an I-type instruction in which you compare the contents of RS and RT. You compare branch when equal, right? So you compare the contents of RS and RT, and then you branch to an address which is provided by this 16-bit offset in words. So you fetch the instruction, right? Whatever is in the PC, that's your address. Whatever you have at that address, move it to the that's your instruction. Then you check for the condition whether those two registers are equal or not. And if it is equal, then you try to calculate the next instruction, right? So if it is equal, then you branch. So PC will get updated by PC plus 4 plus the 16-bit sign extended value multiplied by 4 because things need to be the things are provided as a word offset as opposed to a byte offset. Or else, if the condition did not get satisfied, then you simply go to the next instruction. PC gets updated by PC plus 4. So let's see how the branch operation gets carried out with the data path. So we still have the register file all the way over here. We still have the instruction. We have read register 1, 2. We still have that the sign extender module to go from 16 bits to 32 bits for the 16-bit offset. But now we have a shift left 2, right? What is the purpose of that? Multiply by 4. Perfect. So you're taking this 16-bit offset provided in words You are extending it to 32, then you are shifting left by 2 so that you have multiplied by 4. That is now going to be in bytes, right? So over here it's in bytes. Then depending on how that comparison went, you can either do PC plus 4 or you can do PC plus 4 plus all of that, right? Depending on whether things were equal or not. And how are you controlling whether they are, how are you knowing how are you checking for that condition? Read register read data 1 from register 1, read data 2 from register 2, put them into an ALU, subtract them, and monitor the ALU 0 output. That controls which one you are going to use as the branch target. Either you are going to use PC plus 4 or you are going to use PC plus 4 plus all of that. ALU 0, right, is essentially your 0 output of ALU. So this is the ALU and that is the 0 output. Think of it in separately. This is talking about that. All right, questions here, you guys? The check for comparison is happening over here, right? The condition check is happening here. And the branch address is being computed by that adder. Okay. Let's put it all together because we have got a lot of them. A few of them we added for R-type, then we've added few for load store, then we added a few for branch when equal. Let's try to put it all together so that we will be able to handle all the 8 instructions that we are after. And our target is to be for a single cycle data path, which means that all the 5 steps of the instruction life cycle should be able to be carried out for all these 8 instructions. We are not looking for pipelining just yet. We are trying to make sure that the full cycle gets completed for each of those instructions. It can do all of the above in one cycle. What that means is each part can only be used once per instruction, which means if I'm using the register file or I'm using the ALU or I'm accessing the memory, I can only do one instruction, right? If you think about this, you see over here, there is one stage of register file. There's one stage for ALU. There's one stage for memory access. What I'm trying to do is I'm looking at one instruction going through the entire cycle, as opposed to one of the instruction is you in this particular step while the other instruction is using that hardware. I don't want to do any pipelining here just yet. So some parts may need to be duplicated, we'll see that, and some parts could still be shared using muxes. We'll see that as well. So when we combine the R-type instruction with the load store instruction, we have a mux to stitch them together and we have a mux to stitch them together. Still have the register file, still have the ALU, still have the memory. But now what we have is an ALU source. You see how it changed from 3 to 4 because now we have that one additional bit for ALU source. What is that being used for? Well, in one case, if ALU source is 0, it will pick read register data 2 to go to the ALU, or if ALU source is 1, it will pick the 32-bit field over here, which has been sign extended, to go to the ALU. Well, why do you need one versus the other? Well, if you're doing R-type instruction, which one will you need? read data to or the 32-bit sign extended offset. Read data to, right? But if you are doing load or store, you would need to use this. See that? So you have one more bit, and we are calling that ALU source to control which particular 32-bit number comes to the second side of the ALU. In one case, for R-type instructions, it is going to be one of the 32-bit registers, and in the other, it is going to be one of the it is going to be the 32-bit sign extended offset. You see that? All right. Now, next, what do we have? We have selected the ALU operation. We are doing either the adding or whatever. Then the ALU result, we can write that to the register file, right? You see that ALU result goes through to the mux, and that can be written to the register file, or have an address, you have a write data, you access the memory, you read the data from the memory, and then you can write that to the register. So let's talk about in which case, like the way we drew blue lines and red lines for R-type and load store, let's also try to do that for this. Where should I draw the blue line? R-type to A, which one should I add? So, in other words, memory to register is a select control to either pick read data to go through or ALU result to go through. So, if I want R-type instruction, which means I'm executing R-type instruction, memory to register should be configured so that either the ALU result should go through or the read data should go through, one of them. Which one is for R-type is the question. R-type instructions don't have anything, ALU result. R-type instructions don't have anything to do with the memory. They don't need to go to the memory. They can bypass it. Exactly what is happening, right? That's the ALU result. And when you are doing load or store, you're going to pick this one. Where is the read data? Oh. You see that? So that literally is only for what? The load instruction, right? So when you're loading the instruction, load word, you read from memory and then you go to the register file. Doesn't apply for store word, it only applies for load word. So we have got two muxes over here with two special controls called ALU source and memory to register that allow us to stitch the R-type and the load store data path components. And we're using multiplexers to stitch them together. Okay, let's add one more thing. In this case, we have added something very simple. This is just the instruction fetch circuit. So we still have the register file here. We still have the 32-bit sign extender here. We still have the mux. Still have the ALU. We still have the memory. We still have the memory to register. All of that is there. But now we have separated the memory into two forms. One is data memory. The other is instruction memory. Just so that we can talk about how PC does its job, how the instruction fetch cycle happens versus all the other steps happening. So for the instruction fetch, the program counter is a register which will have the address of the next instruction. So you can just read, you give me the address and you read, that's your instruction coming out, right? So you provide me the address, I will tell you what is that instruction at that address. For the next cycle, PC will get added by 4 using an adder and then it gets updated. So that's your PC plus 4 computation, a separate add by 4, separate from ALU. But now I need to somehow stitch this with what I need to do for the branch when equal instruction, right? For the branch when equal instruction, I need to also consider this to get added on top of that. So I need some more things now. And that's where we are. Now, how do you add the branch address? This was giving us PC plus 4. Now we have another adder. On one of the ends, on one of the inputs, you have PC plus 4. And on the other input, you have the 32-bit sign extended value, which has been shifted left by 2, which means it has been multiplied by 4. You add them together to compute the target address or the branch address. And then you can have another mux to pick the program counter source. That program counter source can either be PC plus 4 getting updated, or it can be when PC source is a 1, it will be the branch address getting updated. You see that? So we are essentially using that adder, shift left by 2, mux, 3 more components here to add the branch address calculation. So PC source would be connected to ALU 0. Why? Let's see. Yes, you're right. That's exactly right. Yes, for BEQ. Yeah. For BEQ only, right? Like that's a special case. That's your full data, a full single cycle data path. Program counter needs to get added by 4. This is your sort of the branch address calculation, register file. You see this mux, this is your register destination. You remember earlier when we were looking at R-type instruction versus load and store instruction, we had 3 registers. In the R-type instruction, we had RS, RT, RD. In the load and store, we had RS, RT, RT, which is why we have that another mux here for that third option. We can either pick RT or we can pick RD to function as our destination register. Let's see, we still have the memory, similar controls, ALU source, we talked about all of that. Just be a little bit careful about how that numbering scheme is. So you might have to refer back to this slide in order to complete the activity. So for example, it's not necessary that the top input is 0 and the bottom input is select line 1. So make sure that you refer to this particular diagram to really look at the specific controls, right? So for example, what does this mean? This particular, if I zoom into here, what does this mean? This is PC plus 4 right here. And then this is the PC plus 4 plus target address, right? Oh no, not target address. This is the total branch address. So this particular diagram says when PC source is a 1, you are updating it by PC plus 4. When PC source is a 0, you're doing a branch address. So just refer back to this. It's not necessary that the top input is 0, bottom input is 1. Let's see. I think that those are it. And this is essentially the same diagram, but with 0 and 1 fixed, right? It's switched. So that the 0 is at the top and 1 is at the bottom, not necessarily for everything. This is the diagram from the textbook, and this is the diagram made on a PowerPoint slide. They are both like identical, just a little bit nicer on the last slide here. So for the activity that you guys are going to work on today, just use the slide number 21 which is also the same as as it is referenced in the textbook. Okay, I think that is all I have. Oh, by the way, I also need to talk about this ALU control, right? So ALU control is another thing that got added here. Let me just take a moment to talk about that. So the five least significant bits of the instruction, 6 least significant bits of the instruction, what are they? Those are for the function code, right? So those function code bits are an input to an ALU control block, which will allow you to find out which particular instruction is getting executed by the ALU. When we start talking about ALU control, when we have a lecture after the exam, you will see why do we need this and how does this play a role. For now, focus on the instruction memory, register file, ALU, the memory, and so don't worry about this particular block just for now. All right, I think you guys are ready for the activity. If you understand the data cycle path and the decisions made to get to this, it should be pretty quick activity.